Hello, my name is Cole Phillips. I am a physics major at West Texas A&M University. Today I will be presenting a lecture on channeling for determining crystal quality in semiconductors and determining interstitial versus substitutional impurities. I'm going to go over a quick overview of what I am going to be talking about. The first thing is, what is channeling? Then I'm going to go over what are impurity semiconductors, how we use channeling to determine the crystal quality of semiconductors, and then finally I'm going to wrap it up with a quick example of an application that uses channeling to benefit semiconductors and other materials. So first, what is channeling? Channeling is a technique used along with Rutherford backscattering spectrometry, or RBS, to determine the properties of materials. If an ion beam is well aligned with the crystal lattice, the ions will be able to pass through the material with very low or zero deflection. This is usually on the magnitude of less than 5%, very, very, very low deflection on very small angles. Okay, so now I am going to go over the 3 requirements for channeling, and I'm going to go into depth on what each of these mean. So number 1, transparency. The particle must find an open channel between the rows of atoms. What I mean by this is, if we can align, for example, an ion beam to our crystal lattice, the ion beam must be parallel to the axis that the atoms lie on, and we must get the particles in between, to enter in between the rows of atoms. So if we set up our ion beam at an angle that is not parallel, it's very likely that we will get Rutherford scattering or other types of scattering, and our angles would be very inconsistent and much larger than what we are wanting. Number 2, steering. There must be a force acting which steers the particle towards the middle of the channel. In this case, we're talking about the positive potential of the atoms that make up the crystal lattice. We can also think of this as the Coulomb repulsion force that's going to keep the atom in the channel. Number 3, stability. The particle must not approach the rows too closely. If a particle gets too close to the atoms of one of the rows of the crystal lattice, the steering effect will take over and overtake the trajectory of the particle, causing it to deflect into much larger angles, and the channeling effect would not be considered. Here is a picture of what I am talking about. We have a lattice made up of sodium atoms and iodine atoms. We have 2 trajectories into the lattice. These 2 trajectories are given by the bold lines. So the first one, we have a trajectory that enters parallel and in between the rows of atoms into the crystal lattice. And if you see by the dotted line, you see it moves in a sort of wave pattern. That wave pattern is the steering effect. Okay, and then on the second bold line trajectory, we will get the dotted line that gets deflected at a much greater angle. That is because the trajectory is not lined up parallel to the axis that the atoms lie on, and so when it gets too close to the atoms of the lattice, the steering effect overtakes them and the trajectory gets thrown completely off what we wanted. Next, I'm going to talk about what are impurity semiconductors. An impurity in a semiconductor is where a certain percentage of a foreign substance is added to the pure substance. Pure semiconductors are usually only useful from a theoretical standpoint. Impurity semiconductors are useful in applied circumstances. The electrical properties of solids are extremely sensitive to even the most minuscule amounts of impurity in the lattice. This could be on the order of 1 part in a billion. And for example, if we have a silicon semiconductor, if we add 10 parts per million of boron to our semiconductor, it will increase the conductivity by 1,000. That is an example of how extremely sensitive the electrical properties of solids are to very, very, very small amounts of impurities. Next, I am going to go over 2 different types of impurities: substitutional and interstitial impurities. Substitutional impurities are impurities that are similar to the host atom. Materials such as brass and bronze have substitutional impurities. A substitutional impurity is when we have 2 atoms in a crystal lattice, and typically the host atom and the impurity are very similar in chemical composition and in overall size. For example, if you have a metal, you have another metal that is close to it on the periodic table. Next, we have interstitial impurities, which are impurities that are considerably smaller than the host atom. These atoms are a little different. They don't take out atoms like superficial impurities do. They're just small amounts of small atoms added to the host atom. And materials such as steel have these impurities. An example of a material that has both substitutional and interstitial impurities is stainless steel. I have a picture here on 3 types of alloys. These 3 types of alloys represent these 3 impurities. Number 1 is not an impurity. It is actually a pure substance. If you can see, it's very even, very symmetric. All of the atoms are the exact same size. Number 2, the substitutional alloy. These have substitutional impurities in the lattice. If you can see, some of the atoms in the lattice are replaced by these blue, smaller atoms. Not much smaller, but they are smaller, and that will change the properties of the alloy. The last one is the interstitial alloy. These have very small atoms added within the channels of the alloy. Unlike substitutional alloy, we increase the total number of atoms in the lattice, whereas in substitutional, we replace atoms in the lattice with different atoms. And as you can tell, these atoms in the interstitial alloy are much smaller, and the effects are much different, especially when we're talking about scattering. Now I want to talk about how we determine the crystal quality of a lattice. We can find how pure a crystal lattice is by using information from RBS and our channeling method. Using channeling, we can align and rotate our material at certain angles to determine the quality of our lattice. What I mean by that is we can run an experiment where we shoot an ion beam at a material. And based on the results of if it scatters or if it passes almost directly through, we can almost map out what our lattice is made of. And we could rotate it slightly to determine how well our lattice is made and how symmetric it is. We could find impurities and determine what they are in the material by noticing scattering effects where a channel in the crystal lattice should be. So, for example, when I was talking about the substitutional and interstitial impurities, when we present different atoms, the Coulomb repulsion force will change when the ions pass by those atoms, and that will affect the trajectory of our ion beam. So when we have a lattice and we shoot our ion beam at it, we should be able to figure out what a pure substance, what a pure lattice, or a pure semiconductor, what our deflection should be. And that should be almost, when it hits a channel and channels all the way through, it should be almost zero deflection. However, depending on how much impurity there are, the deflection can be greater to much greater. Now, a quick application I'm going to go over is ion doping of semiconductors. This is very crucial for modern integrated circuit manufacturing. We could use ion implantation to increase or decrease impurities in semiconductors to make them better conductors or better insulators. And like I said before, we do not have to increase or decrease much. As before I said, the electrical properties of solids are extremely sensitive to impurities. And finally, these are good for developing materials with applications in optoelectric devices, spintronics, and nanophotonics. Now I'm going to conclude everything with a brief summary of what I went over. Channeling is when particles are sent through a channel of a crystal lattice. Along with RBS information of the lattice, we can determine the quality of the lattice. We can use the information given to us by channeling techniques to find impurities in a semiconductor. Finally, with the knowledge of what impurities lie within our semiconductors, we can make our semiconductors better and more useful. So through channeling, we can make better semiconductors. We can determine how the quality of our semiconductor, what it is made of, how much of an impurity there are in our semiconductors. And channeling is the main technique, along with RBS, to find impurities in semiconductors. And we use that information to increase our productivity and efficiency of our semiconductors. And with that, I conclude my presentation. Thank you.